right, good evening, everybody. Thank you so much for coming out. I'm very pleased to introduce our speaker. It's Dr. Ben Davies. He got his undergraduate and Ph.D. degrees at the University of Leeds. He was at the Rochester Institute of Technology for about 4 years, first as a postdoc and then as a research scientist. He now has a Royal Astronomical Society fellowship and is at Cambridge University, not our Cambridge, but their Cambridge, which is a bit of a big deal. And he's going to be talking to us tonight about how supernovae happen. So, Ben?
All right, thanks very much. Okay, everyone. All right. Well, thanks to Dan for inviting me over to sunny Florida. So my talk is about how you make a supernova, and to make a supernova, you need a massive star. And so this talk will be about really the life cycle of those stars. So apologies to people who've already seen this picture today at the science talk. The story will start down here in a star-forming nebula, and we have such a nebula reasonably close by, or close by in astronomy terms anyway. It's about 3,000 light years away, and so it's in the constellation of Orion. So this is Orion, and this is the dude that it's supposed to represent. Here's Orion's belt, so that's quite a famous landmark in the sky, and just below Orion's belt, with the naked eye, you can see kind of a fuzzy blob. And this fuzzy blob is the Orion Nebula. It's a star-forming region. Okay, and as we zoom in, the image quality gets better and better because we're using better telescopes. Okay, so in the Orion Nebula, this is a Hubble Space Telescope image now. In the center of the nebula, you see stars that have already actually formed, as well as stars that are in the process of forming. And the stars that have already formed, the massive ones, they push out on the nebula and evacuate a cavity around those stars. And so what you're seeing here is kind of the inside of kind of a bike helmet type morphology. So this is on the inner, this is the rim closest to us, and then this is the cavity inside. And so lots of stars are forming in that cavity. Now with massive stars, the star formation process happens really quickly. Quickly in astronomy terms anyway, in a few 100,000 years. And it happens while it's still embedded in the cloud. So studying how massive stars form is really tough because you need to be able to see through the cloud and into the core. So I'll just show you an example of this. So this is a patch of that cloud. And if you look in the optical with like Hubble Space Telescope, you see just vague patch of dust. But right in the middle of there's a massive star forming. And if you look in the infrared, you can actually see through this dust into what's going on in the heart of that cloud. So that's what's going on in there. So you suddenly see this thing right in the middle. This is a massive forming star. This is maybe 10 solar masses and growing. And so from a theoretical point of view, from someone who wants to understand this process from the core physics up, it's really tough to study this kind of thing because it's so difficult to see these early forming stages. But people have a go nonetheless. And so what I'm going to show you now is a simulation of a massive star formation in a collapsing cloud. So this giant red thing, this is a simulated cloud. And when I set the simulation running, you'll see star formation happening. Now, what you'll see is gravitational instability. So as soon as you've got a dense region, because it's dense, it has gravity, it draws material in, so it's more massive, and then it has more gravity, and so it's a runaway process. So you'll see, as soon as stars start to form, it goes crazy, and there's just stars flying everywhere. Okay, so here it goes. So as soon as you've got any kind of like filamentary structure, it gets enhanced because it's an unstable process. It has gravity, so it draws more material in, and then just collapses even more. Okay, so now we zoom in, and you'll see the first stars start to form. There's one running across here. There's one, look. on his way across. But in these dense regions here, you see stars are forming, and they draw more material in, which means you've got more star formation going, so it's a complete runaway process. So as soon as you get a few stars forming, it goes completely mad. And you see it's going completely mad by now, and it gets even worse. So I'll just let it run to the end. Okay, so that's where I'm going to stop this particular simulation. So to run this kind of simulation, is really difficult. There's a lot of physics you have to put in there. The resolution that you need, in other words, how small the length scales you need to be able to resolve to do this kind of simulation, mean that to run a simulation like this takes months. It takes like 3-4 months just to run this simulation once. And because it's so hard to do, you have to make approximations. You can't put everything in from the smallest level to the greatest level, because it would just grind to a halt. It would take 10 years to run 1 second. So they have to make approximations, and when you make approximations, you usually get stuff wrong. And moreover, you have to leave things out that you think might not be important, but then it turns out later that they are extremely important. And so what this guy, Matthew Bate, he's a very nice chap, he's very clever. What he left out was this feedback from massive stars. So the big difference between this picture and the Orion Nebula that I showed you before is that in this image there is no cavity. Yeah, you've got stars, material falling in on top of the stars, but there's no cavity blown like you see in the Orion Nebula. Okay, there's your stars, but you've got this big cavity that these massive stars have carved out. So I'm going to show you another simulation now, and this is a simulation where they put the feedback from the massive stars in. So what happens is when the massive star forms, it produces lots and lots of ionizing radiation which push out on the cloud. And so this is an aspect of physics that this guy included in his simulation. So here's your cloud again. This is the top-down view, and this is the same cloud but viewed side-on. And then these two bottom panels are just zooms of the panel above it. Okay, so it's all the same simulation. And when it runs, what you'll see is a star form in the center. You'll see an accretion disk around it, so this kind of disky spinning structure. And then as soon as the star ignites nuclear burning, you'll see it blow a cloud in this right panel. And then eventually you'll see it in a larger scale on this panel here. So I'll just run this one, and you can see what's going on. Okay, so here's the star. It's just formed where that cross is. The accretion disk grows. You'll see it spinning in a minute. Okay, and then watch it blow a bubble in this panel. And in fact, you can see lots of stars forming. And what happens in this simulation is all the extra stars get gobbled up by the big massive one. Okay, so that's the end of that simulation, and you see by the time this is finished, you've got two massive stars in the center with their accretion disks. Okay, so they're still feeding, but they've blown this wind-blown bubble. Okay, so this looks a lot more like what we see in reality. Now, if we were to fast forward this about a million years, you see something like this. This is NGC 346. This is another massive star-forming region, but it's about 1 million years older. This thing's about 2 million years old. And at this stage, all these massive stars in the center are really scraping away at what's left of the natal cloud. And if you fast forward another 1 million years, you get something that looks a bit like this. This is NGC 3603. This is about 3 million years old. And you can see now that the cluster is really, there's nothing behind it. It's naked. You can see everything that's going on in there, and this is what's left of the cloud. This is what's left of stuff that's getting blown away, these two pillars. And so now we've got something called a superstar cluster, what's known in the game as a superstar cluster. So it's young, it's massive, and it's dominated by very massive stars. Now, to study these kind of clusters in our galaxy is difficult because our galaxy is a disk galaxy and we're in the disk. So if we want to see other things in our galaxy, you're looking at it edge on. Okay, so it's like you've got a dinner plate and you're trying to see what the pattern is on the dinner plate, even though you're looking at it from the edge. So if you want to see through the galaxy, so this is the galactic plane, it's the Milky Way. If you want to see superstar clusters in the galaxy, you've got to be able to see through all this stuff that's in the way. So again, you have to switch to the infrared. It's an infrared job. And this cluster that I'm going to show you now is called the Arches cluster, and it's right by the galactic center. So it's in one of the densest regions in the galaxy. So when I set this running, you're going to see a zoom in of the galactic center. Okay, it is the galactic plane, and a zoom in on this region. There's the galactic center there, with a supermassive black hole. And this little smudge is what's called the Arches cluster. Okay, so this is one of the most massive clusters in our galaxy, about 10,000 times more massive than the Sun. And it has lots of these very, very massive stars in it. So you can see the effort that's required to see these star clusters in our galaxy. It's a really tough job. It's much easier to use external galaxies because they're face on. You don't have to fight through all this gas and dust that's in the way. The only problem is they're much, much further away. So this is a star-forming galaxy. It's called M83, and this has lots of these massive star clusters in it. So if we switch to Hubble Space Telescope again and just zoom in on that region. In this galaxy, this has lots and lots of star clusters in it. Now, just for comparison, in our galaxy, we know of maybe 10, 15 very, very massive star clusters. And this is not because they don't exist, it's just because they're really difficult to find. But just looking in this one image, you can easily see just as many star clusters in there. They're all over the place. They're easy to find. Shooting fish in a barrel. So this galaxy is what's known as a grand design spiral. It's very picture postcard looking, very, very attractive. But not all galaxies look like this. And so I always like to show this image. This is NGC 1569. And this is a really tiny star-forming galaxy. It's called dwarf irregular, what's called a dwarf irregular galaxy. And the reason it's an irregular galaxy is because it's so small, but it's actively forming stars. So in this galaxy, you see these two massive star clusters, but this is the whole galaxy. The galaxy is tiny, so it only has two star clusters in it. And these two star clusters are blowing the galaxy apart. You see what's left of the cloud around here. So these star clusters will blow all the gas and dust out of this galaxy. And when it's done, there will be no more star formation after that because there'll be nothing left to form stars out of. Okay, so the massive stars in these star clusters will sit there for about 3 million years. And after 3 million years, something a bit freaky starts to happen in the center of the star. So all stars, when they're on their so-called main sequence, so for the bulk of their life, burn hydrogen. So they burn through, they're powered through nuclear fusion of hydrogen into helium in the core. Now, because helium is heavier than hydrogen, once you've formed it, it sinks to the bottom. So you end up with a core of helium that's just sat there not doing anything. But the more hydrogen you burn, the more helium you get. And at some point, the mass of helium in the center becomes so high, or the pressure becomes so high, that you actually start to fuse helium into carbon. And so when this happens, it's really quite a powerful event. And in only a few thousand years, you'll see a star which was kind of puny suddenly swell up and become completely enormous. And this is due to the helium burning, which is a much more powerful reaction than hydrogen burning. And this causes the outer layers of the star to swell up, and it becomes tens, hundreds times bigger than it was to begin with. So, just for comparison, this is one such star. These stars are called red supergiants. So this is a cartoon of what a red supergiant would look like if it was sat next to our sun. Okay. So I think it's quite a big thing. But I always find it difficult to compare a really big thing with a really small thing. You always need some kind of frame of reference. So here's another way of describing it. This is our solar system. So there's the sun. This is the Earth going around it. And zoom out a bit more. Here's Jupiter's orbit. Here's Saturn's orbit. And if you stuck a red supergiant in the middle of there, it'd look like that. Okay, so I drew the red supergiant with an angry face. And that's because red supergiants are angry. They have a stellar surface which is violent and turbulent. And I've got another movie to show you of what a simulation of a red supergiant surface looks like. Okay, so if you could see such a star close up, this is what you'd see. Now, these stars have convective envelopes, what's called a convective envelope. So you have bubbling gas boiling to the surface and then getting cycled back down again. And so you see this in the sun. The sun is convective as well. But the difference is with a red supergiant, these convective cells are as big as the star itself, which is why it looks like this horrible kind of crazy brain image. And in fact, these convective cells are so big and they're so active, it's difficult to define where the star stops. It doesn't have a defined surface like a basketball. It's just kind of a vague, boiling ball of gas. And in fact, these convective cells are so powerful that they can begin to lift material off the star, and we see it in this object called VY Canis Majoris, which is a very famous red supergiant. And so the actual star is buried in there somewhere. It's just a pinprick. It's not, there is no stellar disk in there. It's just a pinprick of light. You don't resolve the star. But these convective cells are so large and so powerful that they get lifted off the surface of the star and they produce these big kind of bubbly gas arcs that have been lifted off the surface. And so the star is literally ripping itself apart. Now, more massive stars do this in a much more violent way. So this is Eta Carina, which some of you may have heard of. And in the 1800s, Eta Carina blew off 10 solar masses of material in one day. It had a complete freak out. And you might say, how do we know this? Because in 1800, we were all living in caves and howling at the moon. We had no idea about astronomy. But we do have historical records of Eta Carina becoming the brightest star in the sky just overnight, just suddenly switched on, and stayed that bright for 10 years or something like that. And now, 200 years later, we've got powerful telescopes, and so we can look at this object, and we see what was left of that explosion. So this, what's called the Homunculus Nebula, is 10 solar masses of material that all got lifted off the star in one go. And it turns out that about 20, 30 years after that original explosion, there was a secondary explosion that contained about 3 solar masses of material. And if you look deeply in this image, you see a kind of mini version of the same nebula buried in the middle. Incidentally, the reason that this looks so symmetric and nice, and this one is just a complete mess, is that this system's in a very eccentric binary system. And so this controls the shape of the nebula that's blasted off. Now, imagine you had a whole cluster of stars all doing this at the same time. It would completely dominate the output of the galaxy, and this is what we see in M83. So this is a star-forming galaxy. And if you look in certain filters at this galaxy, you see this huge outflow coming perpendicular to the plane of the galaxy. And this is because you've got lots and lots of massive stars all buried in there, all having these explosions, and they join together and form what's called a superwind. In fact, sometimes in some galaxies you can see the material being blasted out and then arcing back and landing back on the disk and triggering more events of star formation further out. Okay, so what happens when the star gets to the end of its life? Well, this is what the structure of a very evolved massive star looks like. So remember at the beginning we had hydrogen burning, and hydrogen burning produces helium, and then eventually the helium core mass grows to be so massive that can produce helium burning, and then you get helium burning with a carbon core. And then eventually the carbon core grows to such a large density and pressure that you get carbon burning, and then that produces neon, and so on, until you get all the way up to iron. And so you end up with an iron core that's just sat there, not doing anything, just getting more and more massive as all this stuff gets turned into more iron. But you can never start iron burning, because iron will not fuse. It's not energetically favorable for iron to fuse in nuclear fusion. And this is because it's an endothermic reaction. So it takes more energy to get two iron nuclei together than it releases when they're stuck together. So actually it's a reaction that requires energy. So it just doesn't want to do that. So you just end up with a big fat iron core just getting bigger and bigger and angrier and angrier. Eventually, the thing just can't support its own weight, and it collapses under its own gravity. And so I'm going to show you a movie of that in a minute, but I'll just explain what happens in this movie. So as the iron core collapses, it's collapsing under its own weight, but at some point, the thing becomes so dense that electrons get forced into the protons to form neutrons, and then the thing is held up by the just power of neutrons just not wanting to go anywhere. It's just a ball of pure neutrons. So it can't collapse any further. But all the stuff that's falling in, it doesn't know that's happened yet, so it just carries on falling in. So it hits this brick wall, metaphorical brick wall. It's much more stronger than a brick wall, obviously. And then it becomes shocked, and then the shock wave just gets bigger and bigger, and then eventually explodes outwards and blows the rest of the star apart. So that's what's happening in this movie now. Okay, so this is the stuff falling in, and this is the kind of surface of this ball of neutrons. But the stuff keeps falling in. All this stuff gets angrier and angrier as this shock wave builds, and eventually it's going to burst outwards. Okay, there it goes. And then we can scale out and watch it keep going. So this is that shock wave bursting out. The material falling in just makes this explosion even more powerful. Okay, so that's what happens when the iron core collapses. And so it's taken about 3 million years to get to this point. And just take note of the time scale there, of this whole simulation. That was 0.4 of a second. So it took 3 million years to exhaust its fuel, and then when it ran out, it took less than half a second to completely blow itself apart. And so if you were watching this, hopefully from a safe distance, this is what you'd see. So you see the flash when all the light gets released, but then eventually you get completely showered with this debris, the envelope that's being blown off, as it rushes towards you at about 10,000 kilometers per second. And so this is something that we've seen happen in real life nearby once. And this happened in 1987 in one of the nearest galaxies to us, the Large Magellanic Cloud. So one day, the galaxy was just sat there, minding its own business, and this little star was there, not particularly an interesting star, no one was that interested in it. And then the next day, that happened. All of a sudden, everyone's interested in it. And so now, how long ago is that? Like 25 years ago, now, 25 years later, we obviously spend a lot of telescope time pointing at this, and this is what we see to be there these days. So that the thing in the middle, that's that's where the star was, and what you see now, this is not the supernova explosion. This little nebula, that's not the supernova explosion. That is the nebula that was thrown off in the years just before the thing went supernova, right? This was already there, and the reason you can see it now is because the supernova explosion lit it up. And so it's all glowing again now, it's not dead. Now if you zoom in on that, so this is where the star was, so you can see the thing still glowing because it's still hot from the supernova explosion. This is the ring, the inner ring of the circumstellar nebula that's been lit up by the supernova explosion. And what you're going to see is a time lapse of lots of images that we've taken of this object over the years, all stacked together. And what you're going to see is all this supernova ejecta, which is streaming outwards. You don't see it because it doesn't emit any light, but at some point it's going to hit this material and it's going to shock it and it's going to heat it up. Okay, so this is what you're seeing now. And yep, there it starts to go. You see these knots of emission suddenly start to glow. This is not this material suddenly deciding to emit light. This is stuff from the center streaming outwards and colliding into this material, and it all just becomes shocked. It becomes like super, super hot. And so that's what we see today when we look at 1987A. So eventually, in about 1,000 years, that object will look something like this. So this is the Crab Nebula. This is a very famous supernova remnant. The supernova went off about 1,000 years ago and was recorded by Chinese astronomers. And this is what we see the object looking like today. So this is all the material that was thrown off as the star exploded. And in the very center, you see what's left. And what you see is a ball of neutrons spinning super fast, okay? Because all that angular momentum when the thing was spinning at, say, 100 kilometers per second when it was alive, all that gets shrunk down, and because you conserve angular momentum, the thing is spinning now at about 1,000 revs per minute. Okay, so it's spinning about as fast as your car does, as car engine does when you're sat at the traffic lights, except instead of being this big, it's like 50 miles across. Okay, even though the star is neutral because it's neutrons, it has a crust, a crust of charged particles. And because this is so dense, it has an incredibly intense magnetic field. So as this thing spins super fast, it's like a dynamo operating, which is driving these shock waves that propagate outwards from the central star. So again, this is a time-lapse movie of what we've seen going on in the center of this nebula for the last 10, 15 years. So, concentrate on this stuff now. So what is this stuff? This stuff is what was thrown out from the core of the supernova explosion. And what happens in a supernova explosion, because you've got so much energy, you get lots and lots of nuclear fusion, like lots and lots. So you take your light elements and you force them together into heavier elements. And so what happens is, in your periodic table, what happens is all these elements get a massive kick. So you've gone from having very little Y, whatever Y is, it's yttrium. From having no yttrium, you've suddenly got loads of yttrium. And from having no calcium, you've suddenly got loads and loads of calcium. So if you take nothing away from this talk, if you forget everything I've said, remember this, right? If you've got no massive stars, you've got no calcium, so you've got no cheese. Does anyone want to live in a universe with no cheese? I know I don't. Although with no cheese, at least you'd never get heartburn, which is a good job because you'd have no magnesium-based heartburn products either. You'd have no chlorine, so your swimming pool would just be disgusting. You'd never want to get in it. You'd have no carbon, so you'd have no carbon-based life forms on Earth. In fact, you'd have no Earth, all right, because you'd have no iron and you'd have nothing that the Earth is made out of. So if it wasn't for massive stars, no clean swimming pools, no cheese, no meerkats, and no planet. In fact, so it's really the way that massive stars govern the chemical evolution of the universe as we know it that makes our lives possible. Okay, so that's the end of the talk. I've gone all the way around this loop from stars forming to the main sequence in star clusters, these post-main sequence phases where they swell up and become extremely angry, supernova phase where they take 3 million years to get there, and then in less than half a second they explode and throw out all the chemically processed material back into the interstellar medium, and then the whole thing starts again. Okay, so I hope you found that enjoyable, if not informative, and thanks very much for listening.